All right, so to get prepared for phase number 2, let me just copy what we ended up with from phase number 1, right? So that would be the array. Okay, looks fine. So let me paste it over here. Okay, perfect. Okay, let me put it here. Right, so that's the array we're gonna start with. We actually got the 3 items already in queue into the queue, right? And we got F over here, and also we got R over here, right? Let's now talk about how we can dequeue 2 times. What we want to do is to dequeue. What exactly should we do in order to dequeue, right? In the case of enqueue, we had to change the R. And symmetrically, in case of dequeue, we gotta change F. And let's see exactly how we change the F. So let's see here. So the idea would be, if I want to enqueue, in that case, ln should be somehow removed. And then I should really move F to the right by 1 position. So F is now pointing to the next item in the queue, right? And I definitely don't want to have the need to really shift everything to the left by 1 position as we did in the fixed size conventional array. Because if we did, what's the point of using circular array, right? So the idea would be we only have to modify F accordingly. That's all we gotta do. Okay, so what we can do is, let me just write it down over here. So we can say F data at index F is simply assigned to be null. Just make sure we clear that. Even though this step over here arguably may not be so necessary logically, because all you do in order to refer to the front of the queue is only by this index over here. Whether or not the position to its left is actually not null or null, in some way doesn't really quite matter. But I would say for cleanness, we better actually assign it to be null. Maybe that element can just be garbage collected as soon as possible, right? Anyway, I would suggest we write this line for cleanness. Okay, and after this, we're simply just going to say F++ over here. And similar to how I highlighted R++ earlier for the enqueue, now for the dequeue, I want you to think about whether or not this F++ will always work, no matter where F is, right? For now, I'm just going to highlight it. You can think about it when you actually completed the exercise by implementing that in Eclipse. I'll just highlight it, okay? Just a question for you, really. Okay, let me make it a little bit bigger over here. Right, let's now move on. Right, so let's now try to do the first dequeue. The dequeue, we are going to assign data at index F to be null. In this case, F is pointing to just ln, so we're going to wipe it out, right? Wipe it out, and also we're going to actually move this to the right by 1 position over here, not the data here. That's the first dequeue. And we want to do another time, right? We want to do 2 times. Okay, for that one there, similarly, we're going to wipe out wherever F is pointing to, and then we are also going to move F to the right by 1 position. That's what we got, right? So now, what will be the size? Let's check very quickly. The size of the array, the size of the queue, the size of the queue. In this case, let me just say over here, the size over here, as we learned before, because now we know that R is greater than F, so we can apply this formula over here, right? So it would be R minus F, which would be 3 minus 2, which is exactly equal to 1, right? So now the size is actually 1, right? Is it full? You can actually check these 2 formulas. I'll let you check it to see whether it's empty. Apparently it's not, because F and R, they are still different. Is it actually full over here? In this case, no, because R circularly going to the next element would be actually index 0. Index 0 is not equal to the F index 2, so that's why it's not full, right? Not empty, not full, neither. All right. I think I might just want to delete this circle over here. It's not really making that clear, right? So that's about the size of the cube so far, right? And there's one thing which I found that I sometimes make some mistake, which I really didn't intend to. When we talk about the size of the array versus the size of the queue, they are different, okay? So let me just make that quick notes over here, right? So when we say the size of the queue versus the size of the array, right? I'm just going to make it over here so that you always remember to distinguish between them. Either we're talking about the queue, or we're talking about the array. Let's say this one here, for example. What's the size of the queue? The size of the queue, you're going to simply apply the formula because R is larger than F. So the size of the queue will be 1. Right? So this will be the size of the queue, right? So I think I can use a circle over here. So this will be the size of the queue. And what about the size of the array? Well, the size of the array, because it's fixed sized, so it's going to be 1, 2, 3, 4, right? And size of the array is actually 4 because it's always fixed, right? So these are the two distinction I would like you to really distinction I would like you to really understand completely. Okay, size of the queue versus size of the array, right? Which is always fixed. Right, so that's about the dequeue. Pretty straightforward. And let's now talk about enqueue. And once we try to do enqueue, we're going to see some interesting stuff that's going to happen. All right, the final phase. Let's now move on to phase number 3. And as usual, let me just try to copy whatever we have achieved from the earlier phase, which would be phase number 2. Let me copy that and set it up. All right. So this will be how we get started on phase number 3, right? Over here. And you can see we got only one item left. And at the moment, to start with, we still have R, we still have F strictly less than R, right? That's actually what we got at the moment. And let's now see how we can enqueue another 2 items over here. Enqueue another 2 elements, okay? And you know what? I think I might just want to move this array over here a little bit down, right? So I got enough space to write something. Okay, good. And let's talk about this one here, enqueue. Enqueue over here. And enqueue, as we did before, we said we should really do these 2 steps over here, right? Let me copy them verbatim to see if there's any change that we need to adapt. We say data at index R is assigned to whatever item that we are trying to enqueue, followed by R++. Right? Let's now talk about it, right? Over here, you can see if I want to enqueue, let's say I want to enqueue 2 names over here. Let's say the first one I want to enqueue will be Suyang, let's say. So data at index R, which will be index 3. So I got Suyang over here, right? This part is okay. However, when I say R++, what I'm going to do is 3++. Well, R storing 3 ++ will be actually 4. So that means R will be pointing to over here. That's actually invalid index. That's not what we intend to do. Definitely not. So that's why I highlighted before for you to actually see if you can think ahead. Right? This is exactly the scenario where we have to so-called wrap around. Right? We want to go circularly when we actually want to move the R index. And we have seen this already, right? That's why the use of the modulo operator is so useful whenever we want to do something circular. Right? So how can we fix this? Well, I'll show you the answer right away. So the way to fix it would be, rather than this one over here, what we should do is R is assigned to R+1. You can think about this part is really the R++, but we want to make sure it goes around the array, goes circularly. So modulo n over here. So that's what we should do. All right. And in this case over here, let's see why it will work. R at the moment is actually 3, right? So you can see 3 + 1 modulo the size of the array will be 1, 2, 3, 4. So that one there is going to be 0. So that means R is going to be reassigned to 0, right? That means we're actually going to move this to here. This is a very critical step I want to make sure you really understand, right? This is so important over here to actually understand about this particular step, right? So I'm going to make it orange over here, right? So far, any lines which are highlighted in orange, they simply are the general patterns that you will need to adopt when you write your Java code, right? May not be all of them, but at least most of them, okay? Right? So whenever you want to update the R, And possibly whenever you want to update the f, you want to judge whether or not you want to use a modulo operator. Whenever you have the need to really wrap around, to go around or go circularly from the end to the beginning, in that case, modulo operator will be your friend. All right. Right. So that's about the first enqueue. Well, the next enqueue will be just standard. Right. Let's do it. Let's say the next one I want to put will be una. Let's say I'll put una over here. In that case, what I would do is I'm going to say r plus 1 modulo n. In this case, since r plus 1 is just going to be 1, which is not larger than or equal to the size, in that case, modulo really has no effects, right? You can think about 1 modulo 4. In this case, is going to be still 1, so we are still okay. So modulo operator will really have its use when you actually need to go around, right? So that's a point I'm trying to make over here. Right, so after this, we're just going to move this element over here to here. All right, of course, I'll put data back. All right, right. So that's about this two enqueue operations. Right, so far so good. And to conclude about this example here, of course, for phase number 3, we need to speak about how we calculate the size of the queue, for example, right? You can still actually talk about whether or not the queue is empty. Apparently not, because R and F, they are not the same. And also, is the queue full? If you actually, well, it is full, because if you try this formula over here, R plus 1 is exactly equal to Q, is equal to F, right? But if you apply this formula over here, okay? What about the size? If you actually simply try to use this formula as before, right? R minus F, 1 minus 2, you're going to get minus 1. That's not right, apparently. So we need a different formula when R is actually not larger than F. In this case, R is strictly less than F, right? That's the final formula we need to talk about, right? Which is not too bad, I can tell you. So the size over here that we want to talk about is this. When R is strictly less than F. So this will be the third case for the size that we need to talk about. We talk about the first case when R is equal to F, simply just 0. When R is larger than F, we do R minus F. What about R is strictly less than F, right? You can definitely see the final formula on the slides, but I'm going to derive it together with you, right? You can think about there are two parts that we want to calculate. This will be the first part, from F until the end, first part. This will be another part over here from the beginning until R minus 1. Agree? Okay, let's now calculate both one by one. So what I will do is I'm just going to actually do, how about use orange over here? You can think about this part over here. This is the one. This is really the interval from index 0 until R minus 1, right? And we'll actually calculate exactly how many numbers are in the interval in just a moment. That'll be the first one. And the second one over there would be actually here. Okay, just make it a little bit smaller. Okay, what about the second one? The second one basically is from F until the length of the array, well, which will be n, capital N, minus 1, the largest index, right? It's going from F until the largest index, which will be n minus 1, like a data the length minus 1, right? How many numbers are here and how many numbers are here? Let's now calculate, right? We know very well about how to calculate the number of elements or numbers in a particular interval inclusive on both ends. That's so important, which I spoke about earlier when we talk about asymptotic analysis. And this one over here will be R minus 1 minus 0 plus 1, right? Which will be equal to simply just R, right? So this will be simply just R. And what about the next one? The next one over here will be n minus 1 minus f plus 1, which will be equal to n minus 1 plus 1 cancel out. It will be n minus f. n minus f over here. Right? You can see it's n minus f over here. And so if you combine these two together, the final answer should be, let me just go back to purple over here. The final answer should be R plus n minus f. So that's the final formula. But of course, you should really know how to derive them. I think so important. I think the process is equally important as the final formula, which you don't really want to memorize, which you might just be mistaken sometimes. Right, let's now double check this formula over here. R is currently just 1, right? So we got 1 over here in this case. In our case, we got 1 and also plus n minus f. What's n? In our case, the array size is simply 4. And 4 minus, and f is now pointing to index 2 over here, and 4 minus 2. And of course, you can do the math. It will just be 3. Right? So that's the final answer, which is really confirming that the formula is working, right? Alrighty, so we talk about the different 4 phases about using the circular array. I believe I cover all the important scenario you should really note in order for you to really complete your implementation, right? So now the exercise will be really up to you. I did my best to really show to you how exactly the circular array work and also derive all the formulas about the size and whether or not the queue is empty or full together with you, right? And make sure you study these slides also carefully. And feel free to actually start from scratch yourself by using a different example, maybe a larger array size, and also try to confirm about the formula yourself. Okay. And finally, let me conclude about the circular array example, circular array implementation. Basically, all the operations we did over here is only about to really use the modulo operation. For example, over here, the modulo operation, and also the modulo operation over here, which is like arithmetic, and also to really do some reassignments, and also to do the reassignment, and also array indexing. Every operation is like that. So that's why in the case of the DQ, we actually got constant amount of time over here. It's a drastic improvement from the fixed size conventional array, in which case we have to shift using a loop, right? You can see that's why we talk about the circular array. Of course, the compromise is you have to deal with the complexity of being flexible on the F and R, which is what I just illustrated, right? So this will be exercise for you. Very important. I cannot really force you to do it, but I would highly recommend you complete it yourself. Create a Java class called circular array queue that implements the queue interface using a circular array, right? And let me just show to you just to conclude. Remember, this is the architecture we spoke about earlier, right? So we already defined the interface for the queue, and we have shown you the code for array queue and also link queue. We show you how to manipulate the circular array, so that it will be your exercise to complete this class on your own. Alrighty, right? So now we are done with discussing the circular array. Let's now move on to the final parts for the queue for the stacking queue ADT, which is about how we can resize the array dynamically.